Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 22 from the course, but make sure you have watched the previous ones before viewing this one. In the last lecture, we discussed about the quantum mechanical model of the atom. And in this lecture, we are going to continue the discussion further and we are going to learn about the quantum numbers. What are quantum numbers? Well, in the simple sense, it would be actually the address of the electron. Just like a person is identified by his address, what place he is living at is given by the address. Similarly, the electron in an atom is completely known by specifying the quantum numbers. So as far as the definition of the quantum numbers is concerned, quantum numbers are defined as the index numbers used to specify the position and energy of an electron in an atom. And the word quantum, this is used to signify that all energy levels which are available to an electron, they are governed by the laws of quantum mechanics. Now there are 4 quantum numbers and each of these has only a specific value and they are all interrelated values. The values assigned to these numbers, they determine specific energies that an electron can have. And each quantum number, this refers to a particular character of the electron. In order to specify completely the position and energy of an electron in an atom, it is necessary to state the values of each of the 4 quantum numbers. So, let us learn one by one what are these 4 quantum numbers. So, the first is the principal quantum number, which is designated by the letter n, and you all have been studying about this n from quite some time now. What is this n? Yes, this is the Bohr's orbit number. So n gives us the number of the energy level, the shell or orbit or stationary state as we may call it, and to which the electron belongs, right? So the n can have any positive whole number value excluding 0, that is n can be 1, 2, 3, 4 up till infinity, and whatever is the value of n, it is going to give the number of that energy level. For example, when n is 1, the energy level or the shell in which the electron is going to be is K shell or the first energy level. Then when n is 2, the energy level is second energy level and this is called as the L shell, and this goes on further. Now, apart from telling the number of the energy level, the principal quantum number helps determine a lot many things that you have studied while we were discussing the Bohr's orbit mathematical expressions. Mathematical expressions for radius, energy, all that you have learned is going to be told by this principal quantum number. So this helps to determine the average distance of the electron from the nucleus. This in terms of quantum mechanics means that it gives the effective volume of the electron cloud. And you know that R, the average distance of electron from the nucleus, this is equal to n square h square over 4 pi k m e square, where Z is 1 for the hydrogen atom, right? Now, this is also going to help determine the energy of electron in an orbit, which is given by minus 2 pi square k square me4 z square divided by n square and h square. And this for the hydrogen atom is going to be minus 1312 by n square kilojoule per mole. And I hope you all remember we have discussed this in a great detail. Now, quickly revising, when n is 1, E1 is going to be minus 1312 kilojoule per mole, and this is the largest value, maximum stability and ground state of the hydrogen atom, right? I hope you remember all of this, and this means that 1312 kilojoule per mole of energy is required to eject an electron from the hydrogen atom, and this is known as the ionization energy. I hope I'm helping you even revise the Bohr's concept. Now, when n is 2, the energy is going to be minus 328 kilojoule per mole, which means that it has become less negative, or we can say there is more energy. The state is less stable with respect to the ground state, and hence it is called as the excited state. And when you see the difference between the two energy levels, delta E, which is En2 minus En1, for example, we have E2 minus E1, this is going to come up to 984 kilojoule per mole. And with increase in n, the energy associated with electron increases, whereas the delta E goes on decreasing. And for n infinity, E infinity is 0. The electron is coming from 0 energy into the orbits, and the energy is becoming more and more negative. I hope you remember this all. Now, the maximum number of electrons in an orbit, this is given to be 2n square. That means that the first orbit can accommodate a maximum of 2 electrons. The second orbit can accommodate a maximum of 8 electrons. The third orbit can accommodate a maximum of 18 electrons. The fourth orbit can accommodate a maximum of 32 electrons. So the next quantum number we have is the azimuthal quantum number L, and this is also known as the subsidiary orbital or angular quantum number. And if you remember, we've discussed about this quantum number as well while we were discussing the Sommerfeld model of atom. While the high power spectroscopes were used, they revealed that the individual spectral lines of hydrogen spectrum, they are composed of groups of closely spaced lines constituting the fine structure. Bohr could not explain this fine structure, so Sommerfeld modified his model, and he said that the orbits which were said to be circular by Bohr, they are not circular but elliptical. And from this he gave the concept of subshells. And he proposed that every shell is composed of subshells having small differences in energy, and they are specified by the secondary quantum number L. And this L is going to now give you the number of subshells a shell can have. The number of subshells in any shell is going to be equal to the number of the n. If n is 3, the number of subshells possible are 3. And what are the values of L possible? These are going to be from 0 to n minus 1. So if n is 3, L can have values 0, 1 and 2, and hence the third shell or the M shell will be having 3 subshells. The subshells, they are also designated by some letters. So if the value of L is 0, the subshell designation is S. When it is 1, the designation of the subshell is P. When it is 2, it is D. 3 is F. 4 is G. 5 is H, and so on. And for the same value of N, the energies of the subshells also vary slightly according to this order, that the S subshell that has the least energy, then P, D and F having the maximum energy in these 4 subshells. And these subshells, they are given the designation SPDF because of these study of the spectra of the alkali metals, and they are named as sharp, principal, diffuse, fundamental orbitals. So that is why S is sharp, principal is P, diffuse is T, and fundamental is F. Now the shape of the orbitals, they can also be given by the value of L. So if the value of L is 0, the shape of the orbital is going to be spherical. If the value of L is 1, the shape of the orbital is going to be dumbbell shaped, and that are the p orbitals. When the value of L is 2 and 3, the orbitals are going to be D and F, and the shape is going to be double dumbbell shaped. And this also determines the angular momentum of the electron, and this is given by the relation mvr is equal to h over 2 pi into under root of L into L plus 1. So this is how you can calculate the angular momentum of the electron as well. Now the number of electrons in a subshell can also be calculated from the value of L according to the relation 2 into 2L plus 1. So the total number of electrons in any subshell is going to be 2 into 2L plus 1. And various designated orbitals and electrons accommodated in them, they are represented as, when n is 1, we have the possible value of L to be 0, and the total number of subshells, this is going to correspond to the value of n. So this is total number of subshells are going to be 1. Okay, we will move one by one. Then n is 2, the total number of subshells is 2. When n is 3, the total number of subshells is 3, and so on. And what are the possible values of L? The possible values of L are going to be 0 to n minus 1. So for n1, we have L0. When n is 2, we have 0 and 1. When n is 3, we have 0, 1, 2. When it is 4, it is 0, 1, 2, 3, and so on. Now the total number of electrons, this is going to be 2 into 2L plus 1. So you can calculate putting the value of L in the relation, and the total number of electrons in the n shell is going to be 2. Then for the second shell, for the 0 value of L, there are going to be 2 electrons. For the 1 value of L, there are going to be 6 electrons, making it 8 electrons in the second energy level. Then for the third energy level, again 0 means 2, 1 means 6, and 2 means 10 electrons, making it a total of 18 electrons maximum, which can be accommodated in the third shell, right? So accordingly you can write the names of the subshells also. When n is 1 and s is 0, you write it as 1s. When n is 2 and L is 0, it is written as 2s. And when n is 2, L is 1, we write it as 2p. Similarly, n3 and L0 is 3s, 3 and 1, it is 3p, 3 and 2, it is 3d, and so on. So I hope the whole chart is clear to you, how for the value of n, we write the value of L, how we write the total number of subshells, the total number of electrons, and how do we denote that particular subshell. So I hope both the quantum numbers, the principal quantum number and the azimuthal quantum number, they are clear to you all. In the next lecture, we would be continuing the quantum numbers further, and we would be learning the next 2 quantum numbers, and then we will see the questions that are formed on these quantum numbers. So meet you again for lecture 23 on the quantum numbers again. If you have any doubts, please mail to us at h2ochemistry@gmail.com. Do subscribe to our channel H2O so that you get a notification as and when we put up a new lecture for you. Also click on the bell icon. If you've liked the lecture, please do click on the like link and stay tuned to our channel H2O. Bye bye for now. Have a nice day. Enjoy yourself.